In this video, we're going to talk about inverse functions. To start this, I would like to look at the relationship of inverse functions. And what I'm going to do is first define two functions which I know happen to be inverses. The first function is f of x is equal to 2x plus 3. I'm going to make a t-table of inputs and corresponding outputs for this function, and I'm going to choose -1, 0, and +1 for my inputs. Now the output for -1 is 1, the output for 0 is 3, and the output for 1 is 5. So I'm going to go ahead and graph these ordered pairs and do the best I can to connect them with a line. So the first point is -1, +1, so it's going to be right here in the second quadrant. Second point here is going to be 0, 3, so it's on the y-axis, which is the y-intercept, and the third point is going to be 1, 5, which is right here in the first quadrant. So I'm going to go ahead and try to connect these as best as I can with a line. I apologize, it's probably not going to look the best, but okay, got that. Alright, so there's my line that goes through those three ordered pairs, and that represents this function right here. I'm now going to go ahead and graph a second function, and I've already told you that this second function is the inverse of the first function here. So g of x is the inverse of f of x, and so I'm going to write this is 1/2 times x minus 3/2. Alright, so I'm going to make a t-table with my ordered pairs and my inputs and outputs. Now my inputs, I'm going to choose slightly different inputs, and I'm doing this for a reason to show you a specific relationship between these two functions. So I'm going to choose 1, 3, and 5, and hopefully you're catching this the relationship right now. The output for 1 is -1, the output for 3 is 0, and the output for 5 is +1, and hopefully you're seeing that relationship right now without me having to describe it. I'm going to go ahead and graph these three. So it's going to be +1, -1. My first order pair is right down here in the fourth quadrant. 3, 0 is on the x-axis, and then 5, 1 is in the first quadrant right here. So going ahead and connecting these with a line. Again, I apologize. I'm going to do the best I can to connect these with a straight line. Got to really focus. Okay, that looks pretty decent. It's not bad. I've had better. Okay, so those are my two lines. And hopefully there's two relationships I want to point out. The first one being this, that if you look at the tables, you notice that I chose the inputs for the second function based on my outputs. And what you see here is that my outputs for the second function were the same as my inputs for the first function. So in other words, to put it simply, the x and y coordinates have been reversed. Okay. The second thing I really want you to notice here, and I'm going to go ahead and draw a line on our coordinate plane to describe this, make it kind of a thick, bold line here. The second thing I want you to see is that that relationship also exists in the coordinate plane. So I drew a third line in here, and you'll notice the third line, the equation is y is equal to x. And the relationship between all three of these lines is that the red line, which is f of x, and the blue line, which is g of x, are reflected across the yellow line. So the best and easiest 2 points to see how they correspond would happen to be the 3, 0, and the 0, 3. You'll notice how these two are reflected across that line, the yellow line, which is the the equation y is equal to x. So again, there's two relationships I wanted you to see. The first one being that the ordered pairs for inverse functions are reversed, and the fact that the graphs of these functions are reflected across the line y is equal to x. So a little different than what we've experienced so far, not across the x-axis, not across the y-axis, but across this line, y is equal to x. In the next set of problems, we're actually going to use the relationship that we just described to find the inverse of these functions. We will not have to graph these, but we will use the relationship we just described. So first thing you need to do is rewrite this in equation form. In other words, replace the f of x with the variable y as your corresponding output. So rewriting this from function notation to equation notation. The second thing we're going to do is to use the relationship that we just described. So notice before we talked about how the x and y was reversed for the functions, for the inverse function. So if we're going to find the inverse of f of x, we want to reverse the variables x and y. So it'll become x is equal to 4y plus 2. The third thing we're going to do now is solve for y. So we will subtract 2 to both sides. So we have x minus 2 is equal to 4y. We will then divide by 4 to both sides. So we get, and I'm going to reverse this, so we get y is equal to x minus 2 all over 4. Now we're going to rewrite this one more time back to function notation because we did want the inverse function, not the inverse equation. Now there's notation for this, and it is f of x is equal to x minus 2 over 4. Now you're saying, well, wait a minute, but this was described as f of x up here, and now this is described as f of x. That can't be. And you're right, that's a problem. So what we do to describe the fact that this is the inverse of f of x is use a little small notation of a -1 exponent. That -1 exponent with the f tells you that it's the inverse of f. All right, so let's go to the second one. We are again going to rewrite with y equals 3x over x plus 2. And we are going to again reverse and switch out the x's and y's. We have x equals. Now everywhere we had x in our previous equation, we are now going to have y. So it will be written 2 places in your numerator and denominator. Alright, now this one's a bit of a trickier problem to solve. We are actually going to multiply both sides by that denominator, y plus 2. That cancels out your denominator. Now we have y plus 2 times x is equal to 3y. Now you might be asking yourself, well, geez, what do I do? Because I have multiple y's and I'm trying to solve for those multiple y's, and I get it. It's a bit of an issue here. So what I recommend doing is distributing the x. That's the first thing I suggest. So let's distribute the x so we can get rid of the grouping symbol. So now we have y times x plus 2x is equal to 3y. Now what I recommend doing is getting all the y's on the same side of the equation. Alright, so I'm going to go ahead and subtract y times x. So now I have 2x is equal to 3y minus y times x. Okay, well, what do you notice is common in both these terms? And that happens to be a y. So we have 2x is equal to, and since they're in common, we can factor them. So it'll be y times 3 minus x. And the last thing we will do is divide by 3 minus x to both sides. So then we have y is equal to 2x over 3 minus x. Now again, we do want to write this in function notation, so we write f and the inverse notation. Remember, the inverse notation is the -1. It is an exponent. It doesn't mean you're actually evaluating f of -1. We are just simply using that as notation for our inverse function is equal to 2x over 3 minus x. We're doing the same thing with problem number 3, but notice problem number 3 has a slight addition to the problem, and that is the notation of x is greater than 0. Now the reason this exists is because if you were to graph f of x, what you notice here, because of the squared, is that it's not actually going to be 1-to-1. Alright, so because this isn't 1-to-1, we restrict the domain of x by saying x is greater than 0, which makes it 1-to-1. So if we left that off, it's not 1-to-1, and therefore could not have an inverse function, could not have an inverse. Okay, so all functions have inverses when they are 1-to-1. All right, so let's go through and do the same exact process we just got done with. So we change this over to y is equal to x squared plus 3 over 3x squared. We then reverse the x's and y's, so we switch them. So this will be x is equal to y squared plus 3 over 3y squared. Okay, well, I'm going to go ahead and multiply both sides by 3y squared to cancel out the denominator here. So now we have 3y squared times x is equal to y squared plus 3. Again, similar to the previous problem, I'm going to go ahead and get the y terms on the same side. So I'm going to subtract y squared to both sides. We can't combine these terms because these are not like terms. I have an x in the first term and the y and no x in the second term. So we just have to write it as 3y squared x minus y squared is equal to 3. Now the next thing I'd like to do is, again, just like with the last problem, you notice how with each of these terms we'd have the term y squared. So I'm going to continue up here. And so I factor the y squared from those two terms, and we have 3x minus 1 is equal to 3. Divide by 3x minus 1. And so now I have y squared is equal to 3 over 3x minus 1. All right, last step, we notice here we have to square root. And so when we square root, we go y is equal to the square root of 3 over 3x minus 1. Now, typically, you're used to doing the positive and negative, so in other words, plus or minus the square root. And we actually don't do that, and here's the reason. If you go back to the original equation, and remember we said that x was greater than 0, well, what will then be the range? The y value in this case will always be positive as well. So the y in this case will always be positive here, which means that this is always positive and no negative. All right? So in other words, we can't have the negative square root. All right? That doesn't exist in our inverse here. So to rewrite this one last time, because again I do want to write this in function notation, I'm going to go ahead and write f inverse of x is equal to the square root of 3 over 3x minus 1. And that is your inverse function to the original function f of x equals x squared plus 3 all over 3x squared.